What happens if you drop an ant from the Empire State Building? It is a classic question, a fun thought experiment. Does the tiny creature plummet to its doom? Does it float down gently like a seed on the breeze? Or does something else happen entirely? This feels like it should have a simple yes or no answer, but the journey to that answer is where the fun is. Let's dig in and find out the truth. We'll put the idea to the test, not by actually dropping an ant, but by using the power of science. We'll look at physics biology, the unique environment of a massive city, a deep dive into forces that govern our world, from the grand scale of a skyscraper to the tiny scale of a single insect. We'll explore the air, the speed, the size, the landing, a puzzle with many pieces. We'll put them together one by one until the full picture is clear. The journey begins with this bold question. We will not just skim the surface, we will go deep. There's a common story you might have heard. It is a piece of popular science folklore that gets passed around. The story goes that an ant could be dropped from any height, even the top of the Empire State Building, and it would walk away completely unscathed. The myth says the ant is just too small and light to get hurt. It doesn't build up enough speed to create a dangerous impact. It sounds plausible, right? It feels intuitively true. We see tiny things, dust motes, float around without a care. But is it actually true, a scientific fact, or just a good story we like to repeat? Myths like this are fun, but as Mythbusters, our job is to separate facts from fiction. We are not here to guess, we are here to know. The promise is this: we'll test the idea with simple, clear facts. We won't leave any stone unturned. We'll follow the evidence wherever it leads, whether it confirms the old story or reveals a shocking new truth. We will be methodical and thorough, ensuring our conclusion sits on a solid foundation of real-world principles. First, let's talk about falling. When something falls, gravity pulls it down. Unopposed, it would just keep going faster, and faster, and faster. But here on Earth, things are not unopposed. There is something in the way: the air. Air is made of countless tiny particles. When you fall through it, you have to push those particles out of the way. This creates a force pushing back up on you, air resistance, or drag. The faster you go, the more air you push aside each second, the stronger that resistance becomes, like sticking your hand out of a moving car window. This brings us to a very important idea: terminal velocity. Terminal velocity is reached when the force of gravity equals the force of air resistance. Imagine you have just jumped out of a plane. At first, gravity is winning. You accelerate, picking up speed. But as you go faster, air resistance pushing up gets stronger and stronger. Eventually you reach a speed where upward push exactly balances gravity. At that exact moment, the forces are equal. You stop accelerating. That steady maximum speed is terminal velocity. What determines it? Two big things: mass, surface area. Think of a heavy dense cannonball. It has lots of mass. Gravity pulls hard. It's round and compact. Small surface area. It must fall very fast before air resistance balances gravity. Its terminal velocity is very, very high. Now think of a feather. Very little mass. Weak gravity pull. Wide, complex shape. Huge surface area for its weight. Air gets a great grip on it. This is the key. The relationship between an object's weight and its surface area is what really matters. Small objects have much larger surface area relative to their tiny weight. As you shrink an object, volume and weight falls faster than surface area. A fundamental rule of scale. A single raindrop can fall fast enough to sting. A cloud of mist just hangs in the air. Mist droplets are so tiny their weight is almost nothing compared to air resistance. Their terminal velocity is incredibly low, so they float. Let's apply this science to our subjects: a human and an ant. First, the human. Dropping something in the real world is not like dropping it in a sterile laboratory vacuum. The environment of a massive city like New York adds a whole new layer of complexity, especially around a colossal structure like the Empire State Building. Skyscrapers are not just tall, they are giant obstacles that disrupt the flow of air. Wind hitting the face of the building has to go somewhere. It gets pushed up down around the sides, creating a chaotic mix of currents. There are powerful updrafts, swirling eddies, unpredictable gusts that form in the urban canyons between buildings. For our tiny, lightweight ant, these air currents are not a minor detail. They are a dominant force. While a falling human would slice through most of these winds due to their momentum, the ant is so light that it would be completely at the mercy of the air. A strong updraft could actually slow its descent or even lift it up for a moment. A sideways gust could blow it far off its original course. The ant would not fall in a neat straight line. Instead, it would be carried on a wild, meandering journey drifting left, right, up, down like a piece of ash from a fire. After its long, winding journey down, our ant must finally land. The nature of the landing surface is the next critical piece of the puzzle. What could the ant possibly land on in the middle of a city? The options are varied, ranging from the forgiving, it could land on a patch of grass in a nearby park, a pile of soft dirt in a planter box, the leafy canopy of a city tree, to the firm. In any of these cases, the landing would be incredibly gentle. The surface itself would cushion the already minimal impact. The ant would simply touch down, reorient itself, and walk away. But what about the most likely scenario? A hard, unforgiving surface like concrete or asphalt. This is where the ant's biology provides its final brilliant line of defense. First, remember the impact speed is only around 4 miles per hour. This is a very low-energy collision. Second, the ant has an exoskeleton, a hard external skeleton made of a tough material called chitin. It acts like a full-body suit of armor, distributing force across the whole body. It is incredibly strong for its size. The ant's body is also built to handle jolts. Its 6 legs are jointed and flexible, acting as tiny shock absorbers. When it lands, the legs bend and flex, dissipating the energy before it reaches vital organs. So, we have established that the fall itself, the impact with the ground, is not the primary danger. But surviving the fall is not the same as surviving the city. The moment the ant lands, it enters a new and challenging environment. The real gauntlet begins after the landing. The greatest threats are not from the laws of physics but from everyday urban hazards. A slow-drifting, tiny insect is a perfect bite-sized snack for any number of predators. Imagine the ant's journey down, passing building windows, passing ledges. It could easily encounter a spider's web. A spider would not hesitate to wrap up such an easy meal. In the air, a passing bird could spot the tiny speck and snap it up mid-flight. Swift sparrow. The slow, predictable descent makes the ant an easy target. The height of the building means a longer time spent in this aerial danger zone, increasing the probability of an unfortunate encounter with a hungry predator long before it reaches the pavement. Even if the ant successfully lands on the sidewalk, its ordeal is far from over. A busy New York City sidewalk is a minefield. Thousands of pedestrians walk these streets every day. A single footstep would mean instant annihilation, a risk far greater than the fall itself. The ant could land near a busy roadway and be crushed by a car tire or blown away by the gust of a passing bus. It could be washed into a storm drain during a sudden rain shower, a place from which escape would be nearly impossible. Or it could land on a hot, dark asphalt roof on a summer day and quickly perish from the heat. So, after examining the science, the environment, and the biology, we can finally answer our big question. What happens if you drop an ant from the top of the Empire State Building? The shocking truth is that the myth is, for the most part, correct. The ant would survive the fall itself. The combination of its incredibly low mass and its relatively large surface area gives it a very low terminal velocity. It would never fall fast enough to be harmed by the impact with the ground. The physics are clear and undeniable. Air resistance is the great equalizer for tiny creatures. An ant reaches its maximum speed of just a few miles per hour after falling only a short distance. From that point on, additional height doesn't increase impact speed. It simply floats, drifts, and tumbles its way down. Whether it lands on soft grass or hard concrete, its tough exoskeleton and jointed legs are more than capable of absorbing the minuscule shock of the landing. The fall itself is not a deadly event. Our investigation showed the building's height is irrelevant to the ant's impact speed. Dropping it from the 100th floor or the 2nd floor gives the same gentle landing. The real dangers aren't from gravity but the world around it. Therefore, definitive answer, yes, an ant can survive the physical impact of a fall from the Empire State Building. However, overall survival isn't guaranteed because of many environmental hazards during and after descent. The ant will not die from the fall, but it might not live to tell the tale.